Welcome to G Fun Facts Online. In the palm of your hand, a universe of information, entertainment, and connection thrives. Your smartphone is a testament to technological progress, but beneath its cool exterior, a fierce battle is being waged, a war against heat. Every text, every video, every game generates a thermal onslaught that threatens to slow down, damage, and ultimately destroy the electronics within. This is the story of that battle, and the silent, microscopic heroes at its front line, the advanced materials engineered to keep our gadgets running cool. The ever-increasing power and shrinking size of our devices have made thermal management one of the most critical challenges in modern engineering. The physics is simple. The flow of electrons through billions of transistors encounters resistance, and this resistance generates heat. The more powerful the processor, the more heat it produces. And with components packed ever more tightly, that heat has nowhere to go. The consequences range from a laggy user experience due to thermal throttling, where a device slows down to cool off, to catastrophic component failure. For years, the answer was fans and bulky metal fins called heat sinks. But in an era of paper-thin laptops and pocket-sized supercomputers, these solutions are often too large. The future of cooling relies on a more elegant, passive approach, one rooted in materials science. Scientists are in a race to perfect materials with extraordinary thermal properties, creating an invisible network of thermal highways that channel heat away from critical components. Let's dive into the foundation of cool. Thermal interface materials, or TIMs. These are the unsung heroes that bridge the microscopic gaps between a heat-generating component, like a CPU, and its cooling apparatus. Even the most polished metal surfaces are, at a microscopic level, a landscape of peaks and valleys. When two surfaces are pressed together, tiny air gaps are formed. Since air is a terrible conductor of heat, these gaps act as an insulating blanket. TIMs are designed to fill these gaps, creating a continuous path for heat to travel. The most common TIM is thermal grease or paste. This viscous substance, often a silicone or hydrocarbon base filled with thermally conductive particles like metal oxides, is applied as a thin layer between the processor and its heat sink. Its primary advantage is its ability to create an extremely thin bond line, minimizing thermal resistance. PC builders are intimately familiar with applying a pea-sized amount of thermal paste to a new CPU. While effective, thermal pastes can dry out or be squeezed out over time due to heating and cooling cycles, reducing their effectiveness. High-performance pastes from companies like Thermal Grizzly are designed for long-term stability to combat this. For applications where a paste is impractical, thermal pads offer a clean alternative. These are soft, preformed sheets of silicone filled with conductive materials. They are easy to apply and come in various thicknesses to bridge larger gaps, commonly used for cooling memory chips and power regulation modules. However, this convenience comes at the cost of some performance, as they are generally thicker than a layer of paste. Innovations like the Thermal Grizzly CryoSheet, a graphene-based pad, are closing this performance gap, though at a higher cost. For the ultimate in thermal performance, nothing beats liquid metal. These alloys, typically gallium-based, are liquid at or near room temperature and offer thermal conductivity an order of magnitude higher than the best pastes. They provide the lowest possible thermal interface resistance, making them a favorite among extreme overclockers. But this power comes with challenges. Liquid metal is electrically conductive, meaning any leakage could destroy a device. It can also be corrosive to certain metals, like aluminum. Companies like Indium Corporation have developed patented systems to ensure containment and compatibility. Liquid metal is no longer just for enthusiasts. Sony famously uses liquid metal for the powerful processor in the PlayStation 5 and will continue to do so in the PS5 Pro. This allows for efficient heat transfer to the console's massive cooling system. High-end gaming laptops from Asus ROG also use Thermal Grizzly's Conductonaut Extreme Liquid Metal, claiming it can lower CPU temperatures by up to 15 degrees Celsius compared to traditional pastes. Once the heat is transferred away from the chip, the next challenge is to spread it over a larger area for dissipation. This is the job of a heat spreader. In a smartphone, this is the primary method of cooling. One of the most remarkable materials used for heat spreading is graphite. In its pure crystalline form, graphite is a thermal superstar. It exhibits a property called anisotropic thermal conductivity, meaning it conducts heat differently, in different directions. Its thermal conductivity along its surface can be 4 to 5 times higher than that of copper, while its conductivity through its thickness is much lower. This makes it perfect for a heat spreader. When heat from a processor hits a thin graphite sheet, it spreads out rapidly across the sheet, transforming a concentrated hotspot into a much larger, cooler, warm surface. This prevents throttling and makes the device more comfortable to hold. Most modern high-end smartphones, including many Samsung Galaxy models, use graphite heat spreaders. When it comes to thermal conductivity, however, one material reigns supreme: diamond. A synthetic diamond heat spreader can have a thermal conductivity of over 2,000 watts per meter Kelvin, more than 5 times that of copper. This unmatched ability to move heat makes it ideal for the most demanding applications, like high-power radio frequency devices and lasers. Diamond is also an excellent electrical insulator, lightweight and durable. The main barrier to its widespread use is, of course, cost. In devices with higher power densities like gaming laptops and consoles, we need more advanced solutions: heat pipes and vapor chambers. Both operate on the same principle of phase change cooling. Inside a sealed copper enclosure, a small amount of a working fluid, usually deionized water, is in a partial vacuum. When heat is applied, the fluid evaporates. This vapor travels to a cooler part of the enclosure, where it condenses back into a liquid, releasing its stored heat. The liquid then returns to the hot side via a wick structure, and the cycle repeats. Heat pipes are long, thin tubes, excellent at moving heat along a linear path. They are ideal for transporting heat from a laptop CPU to a fan at the edge. They are inexpensive and can be bent to fit into tight spaces. Samsung used water-filled copper heat pipes in their Galaxy S7, S8, and S9 smartphones. A vapor chamber can be thought of as a flattened heat pipe. Instead of moving heat along a line, it spreads it over a two-dimensional surface. This makes them extremely effective at cooling large, high-power components like high-end CPUs and GPUs. Vapor chambers are a key component in the cooling systems of both the Xbox Series X and the upcoming iPhone 17 Pro. In the Xbox, the vapor chamber is part of a complex architecture that distributes cool air through different zones of the console. For the iPhone 17 Pro, the vapor chamber will work with the device's aluminum body to dissipate heat from the powerful A19 Pro chip. Gaming laptops from brands like Razer and Asus also heavily rely on vapor chambers. The world of thermal management is constantly evolving. Let's look at the cutting edge. Phase change materials, or PCMs, are substances that absorb and store large amounts of heat as they change from a solid to a liquid, like waxes or salts. The idea is to use a PCM to absorb heat during intense activity, like gaming, and then release that heat slowly when the device is idle. This can help smooth out temperature spikes and prevent throttling. Then there are thermoelectric coolers, or TECs, also known as Peltier devices. They are solid-state heat pumps that use an electric current to move heat. When a current passes through the junction of two different semiconductor materials, one side of the junction gets hot while the other gets cold. This allows for active cooling without any moving parts. TECs are already used in niche applications, and in consumer electronics, they are being explored for spot cooling. Researchers at Rutgers University have shown that a graphene-based TEC can achieve a power factor about 2 times higher than previous designs. At the nanoscale, materials exhibit extraordinary properties. We've seen graphene's incredible thermal conductivity. Carbon nanotubes, which are essentially rolled-up sheets of graphene, also have exceptional thermal properties. Researchers are working on integrating these materials into everything from TIMs to heat sinks. A partnership between Dow and Carbice is focused on combining silicone with aligned carbon nanotubes to create advanced thermal interface materials. Finally, 3D printing is revolutionizing the design of cooling systems. It allows for the creation of heat sinks with incredibly complex geometries optimized for airflow and heat transfer, enabling custom solutions that are perfectly tailored to a specific device. The silent war against heat inside our devices is a testament to the power of materials science. From humble thermal paste to exotic synthetic, diamond, and graphene, an arsenal of advanced materials ensures our gadgets run cool and at peak performance. These innovations are not just about preventing our phones from getting warm. They are about enabling the next generation of technology. As we move towards a future of more powerful AI, ubiquitous 5G, and immersive virtual reality, the demands on our devices will only increase. We can expect to see wider adoption of technologies like vapor chambers and liquid metal, and the commercialization of phase change materials and thermoelectric coolers. The promise of nanomaterials and 3D printing will unlock new possibilities we are only just beginning to imagine. The next time you pick up your smartphone, take a moment to appreciate the invisible world of materials science at work. It is a world of constant innovation, paving the way for a cooler, faster, and more powerful future.